Hello, everyone. Thanks for coming today to this PhD seminar. It's my pleasure to host today Rafael Va from University of Seville. Thanks, Rafael, for coming and sharing your knowledge with us today. Rafael has a background on electrical engineering and mathematics, so he got the 2 degrees from University of Seville. And then he moved to San Diego, to California, to pursue a master and a PhD in aerospace engineering. He was passionate about, as far as he told me, right, that he wanted to move into space, and he actually got a PhD in that branch. Then he moved back to Seville, and now he's a full professor at the Department of Aerospace Engineering, where he's teaching for 15 years now orbital mechanics, attitude dynamics, and I guess other subjects. He has more than 150 journal and conference papers in different topics of guidance, navigation, control, space surveillance, awareness. He's associate editor of 2 important journals in control field, like Automatica and the EEE Systems and Controllers. And he's also a member of IFAC, the International Federation of Automatic Control, and the Aerospace Control, and the EEE Technical Committees on Distributed Parameter Systems. All in all, he's going to be talking today about model predictive control. I don't know if you are aware, but University of Seville is one of the top schools in model predictive control all over the world. So it's a pleasure to have you here today. Thanks very much for coming.
Okay. Well, thanks. First of all, thanks a lot for the invitation and the opportunity to give this talk. It's always a pleasure for me to come to Carlos III. I've been here many times, but not giving a talk. This is the first time, so I hope it's not the last. Okay, well, I'm going to share here some research from the past. Actually, it's what I'm going to talk to you about, so I need to credit many co-authors, mainly Francisco Gavilan and Julio Sanchez. They both did their PhD with me. He's now a professor at our department, and he's a postdoc. He got a Marie Curie postdoctoral position. He was in Colorado for 1.5 years, and now he's in the return phase and coming back to us in Seville. Then Eduardo is very well known in predictive control. Christophe, professor from Toulouse. Michael Hart from Boeing, and that will be the last thing I will present. Some research we did in MPC with Boeing. Okay, let's see if it moves. Now it doesn't. Okay, now it's working. Okay, so I have too many slides, so I will try to skip some, but I would like to talk to you about spacecraft rendezvous. Is the main topic I have been working on since I went to Seville applying MPC to the problem of spacecraft rendezvous. This is the close encounter between 2 spacecraft. Then I will show to you how you can combine MPC with other control algorithms, such as flatness. And then also 2 other applications for UAVs, which I think are also interesting, and show how MPC is a transversal tool that you can apply to many things. So the most important, I don't know why it works, and then it stopped working, and then works again. I had to be close, maybe? Maybe I have to point. Okay. Yes? Okay. So first of all, I'm going to be talking about MPC, and then a few advanced ideas to use MPC for spectral rendezvous, but also robust MPC. I will explain to you what that idea is. And also using a more realistic model of thrusters that makes the problem more challenging. Okay, so this is the outline. First of all, I will introduce what MPC is, which I think is the most important thing for all of you. Then talk a little bit about rendezvous, and then the specific application, and then finally the part of thrusters. Okay, so what is MPC? Okay, so the idea of MPC is it's very much the way we work in life, in the following sense. So in MPC, what you do is solve an optimal control. So that's what you do in life. You think about something you want to do. For instance, you want to drive to somewhere. So in your head, you think about what is the most optimal way to go there in terms of time, fuel, or whatever is your optimization criteria, right? Now you start driving, and of course, you don't drive with your eyes closed, right? I hope. So you start driving, and then at some point, something that you were not expecting happens. You see some traffic, and what do you do then? Okay, you start thinking again, okay, maybe I should go this other way to avoid the traffic. So you are replanning. And that's the main idea of MPC, replanning. Of course, nowadays, you don't do it in your head, you do it with the phone and Google Maps, that's true. But in any case, that's the point. You want to go from here to there, you plan an optimal way of doing it, right? But then you start applying the control, and maybe your model is not perfect, you have some perturbations. So instead of going where you expect in your optimal plan, you go to a different point. So now you replan. That's the concept, nothing more difficult than that. But of course, to pose it is a bit more difficult. So here are the 4 typical steps, and let me also tell you about this book. It's a great book. It's not too advanced, but very good to start with. It's a reference from 2 professors at the University of Seville, and they really got so many citations out of the book that I'm so jealous. They have more citations there that I have for all my career. So good book, very good book to start with. So imagine you have some kind of dynamical system, typically continuous. So the first step will be to discretize it. So you can pose an optimal problem that you can solve. Typically for a finite number of intervals, what is called the time horizon. And I mean, this is not really necessary. There are other ways to do it, but you can, for instance, assume that your inputs are constant. Now the idea is, using this model, you can predict the state based on where you are now and the inputs you are going to apply, which you need to compute. Then you do the optimization, and you find all the optimal controls you should apply to arrive to your destination, minimizing your objective function. But you only apply the first. That's the key. You apply the first, and then now you are in a different position. That will be your new initial condition, and you go back to optimizing the inputs. You are repeating this procedure. And this is what is called a receding or sliding horizon. And this is the main concept in MPC. It's the main difference with the typical optimal control, which is open loop. Here you are closing the loop by repeating the optimization. Okay, so here is an example for you to see these concepts in action. Imagine you have this simple linear system. Maybe you can say this is very simple, but in Rendezvous, actually, the easiest model is like this, as you will see in a moment. So you discretize the time, and then you go to discrete time by solving the linear equation using exponential matrices, which we will see in the case of Rendezvous, you can solve explicitly for A and B. And, now you can recursively not only say what will be the next state, but also the state after J steps. So you recursively apply this formula, and then you find that the state at the future is a function of your state now. This is the initial condition, and all the inputs that you need to apply at the next steps. And you can write this in this way. And now you also have to take into account, and this is a very interesting feature of MPC that you don't have with some other control algorithms, that because everything is based in optimization, you can consider all kinds of constraints, and even some kind of terminal constraints, which could be inequality or equality. Of course, equality, you have to be careful because sometimes you cannot find a feasible solution. But in any case, you could, in principle, pose it. So you have some constraints in the state and in the actuation, and then perhaps some terminal constraints. And then you have to have some objective function. Now, using this prediction that I showed you in the previous slide, all the constraints can be put in terms of the inputs. So in the end, you have a fine-dimensional optimization problem that you can solve in principle if everything is linear, like you see here. In MATLAB, you could do it with quadprog, limprog, depending on the objective function. The objective function is quadratic. The constraint is linear. You use quadprog. If the objective function is linear and the constraints are linear, you use limprog. And of course, if it's non-linear, there are other ways to do it, but it becomes more difficult. Now, what you do is you apply the first control you computed, and as I say, now it's not it can happen that the model dynamics, the perturbation, the uncertainties, whatever, make the prediction to fail, and you don't end up where you expected in the first step. But that's okay. You close the loop, and what you do in MPC is you discard these pre-computed values and repeat the optimization starting at x of 1. And then you repeat and repeat and repeat this idea. And that's the key of MPC. Okay, so what's the advantage and what are the disadvantages? Okay, well, first of all, it's optimal. And some people, probably every one of you know about PIDs. It's the most basic controller. Some people say that the comparison between PID and MPC, PID is like driving only looking at the rear mirrors, which is not a great idea. Whereas driving with MPCs, I mean, you look everywhere, right? So it looks into the future. It's optimal. You can consider constraints, which is, I mean, there are many great approaches in control, but many of them are not able to consider constraints, which is a big issue. And gives you a good performance because it's optimal. And you can also include disturbances, as I will show you later in the presentation. But of course, if your system is nonlinear, all that I said before becomes harder, and you require more and more time to compute this optimal input. And you need to do it in between. I mean, you are moving, you end up here, and you should be able to very fast compute a new controller. And that could be a problem if your system is nonlinear, of course. It's a control method that has been used really, really widely in the process industry, in chemical plants. And there are even companies that all they do is install an MPC in your chemical plant and tune it and make it work for you. That's the line of business. Because when they started implementing it, they really got a lot of savings. But nowadays, 20, 30 years ago, we couldn't dream about something like this, and not because it's Apple, but because the processing power is it's really amazing what we can do today. So now, MPC is emerging as a feasible technique in aerospace, right? Of course, spacecraft rendezvous in particular is a great example because it's slow, as we will see in a moment, and it's also linear. Could be linear time invariant, as I showed you before, but also linear time invariant, depending if we are considering spacecraft with eccentricity or with no eccentricity. So let me move into rendezvous very quick. Here you have the rendezvous between Apollo and Soyuz in 1975, the year I was born. This was the first joint US and Soviet mission, right? And they docked during 2 days. So we consider 2 vehicles. Of course, you could consider even more. One of the spacecraft is known as the target vehicle, or just target, but there are other names. The chief, I don't remember now, but you see many names in different books, right? And the other is the chaser. I like this target and chaser because it's quite visual. They already use, I should say, chief and deputy, and there are others. Leader and follower, I think, is another. And the chaser is the one that can maneuver and starts from a known position and wants to go to the target. Rendezvous must be done with controlling position and in velocity. Of course, you could maybe controlling the position, and then we are talking about interception, which could be of interest if you are working in the military, right, to destroy a satellite. But we will be very peaceful here and consider controlling both parts. But it's true that if you learn to do rendezvous with control position and velocity, you could do only in position and apply this to other ideas. Okay, let me just give you an overview in history. The first rendezvous was tested in 1965 for the Gemini missions, and they did it for Apollo. In Apollo, it was crucial to have the capability of doing rendezvous to reduce the mass. So a critical part of the mission to the moon was the rendezvous between the command module and the lunar module. And they already had prepared, well, many things could fail, but this was one of the big ones. And as you know, they had even prepared this course to say in case it failed. It was all prepared because they didn't know if it was going to work. They had tested it a few times in Earth orbit, but never in moon orbit. And the interesting thing about this rendezvous performed by the Americans is that was manual, was not automatic. So the astronauts were performing the maneuvers they were trained to do it. What about the Soviets? They had an automated approach as early as in the 67, but they require a very complicated set of antennas in both vehicles. Then later, they improved, and this is the modern Russian rendezvous system. It's called Kurs, which means Kurs system, and they use it for rendezvous with the Mir. And it does not require the target cooperation as the early system, but it weighs a lot. What about the space shuttle? They also did it manually with small hops, as you can see here. So this part, the final part of the rendezvous, was performed by the astronauts, slowly maneuvering the vehicle, and they had two ways of doing it, depending on if they approach from the radial direction or from being in the same orbit but with a slight phase angle. You could approach the vehicle very slowly. So that were the two ways to approach using rendezvous. What about us? We also had our system. It was created for rendezvous with the ISS, the ATV, Automated Transfer Vehicle. And so far, I think it was, I think it's discontinued, right? But they were like five spacecraft. And it didn't require the cooperation, but of course, it required specific equipment in both sides. I had like a very complicated mission profile you had to approach in a very specific way just to be sure and safe. Okay, now rendezvous. Here is a good reference if you are interested in the topic. And it has 4 phases. First, of course, you need to launch the chaser from Earth or maybe a different orbit, whatever, and get more or less close. You are from 10 to 100 kilometers close, and then the far-range rendezvous starts. That's not too difficult because you don't care too much about safety, right? You are far. So typically you use relative navigation, and then what is really interesting is the close-range rendezvous. Because here you want to get really, really close, maybe at 1 meter distance from the target, and centimeters per second relative speeds. And depending on the mission, you may want to perform a docking or berthing. If I remember correctly, when you dock, you become one with the target, whereas berthing is more like having some kind of flexible attachment to the target, which makes, of course, you can have some instabilities, whatever, but it's something temporary, whereas docking can be permanent if you want. Okay, so we concentrate on the close range rendezvous. Now, there are many models, but we will concentrate in the simplest possible one, which is also very applicable because there are many spacecraft in circular orbits. So we consider the target in a circular orbit, zero centricity, around central body, typically the Earth, a passive target, and less than 1 kilometer the chaser, so very close. So you can apply some linearization techniques that work quite well. I mean, you can compare the dynamics, and they are basically the same when you are so close, the nonlinear and linear dynamics. Now some nomenclature, let's call R the distance from central body to target, mu the gravitational parameter. So in the end, your only parameter becomes the angular velocity n, which as you know is actually the angular speed of the target. And a small case r is the position with respect to the chaser. So these are your equations, particularly when you write them in this LBLH frame. It's a local frame in which here you see the x direction points in the same direction as r. The y goes in the direction of the velocity, and z out of plane. And it's just quite a simple model, as you see, linear, but works excellently. I mean, you can compare with the nonlinear dynamics of the two-body problem, subtracting target from chaser, and compare with this, and you will have deviation of centimeters, right? When you start very close. I said at the beginning, initial distance of about 1 kilometer, right? Okay, now what are the constraints? We're going to apply MPC. We have already our model, so we have to talk about the constraints a little bit. Some limitation in the thrust, and then the mode of operation. I will talk about this later. I don't want to run out of time, so I will go a bit fast. Avoid collisions. Typically, you approach inside what is typically called a line of sight, so the sensors are in view of each other, which helps for safety as well. I will not include this in the talk, but you can consider safe trajectories in case your engine fails. Hopefully, you will be in some trajectory that doesn't collide with the target. That's possible. It has been studied, but I will not consider that in the talk. Also, a very interesting case is if the target's attitude changing with time and you have this line of sight, is the line of sight is rotating. So you should be able to follow it as well. And of course, you want to have some economy considerations, so you will optimize fuel consumption. Okay, this is a line of sight. I mean, there are several ways to pose it, but here we pose it as a kind of, I mean, if you cut it by planes, it's like a rectangular region that is growing. It's a kind of a pyramid, right? And it can be described in a linear way, which helps in the optimization. Then for the actuation, there are two ways of actuating. You can consider that you can establish any kind of level of force in a given range by using electrical propulsion, for instance, or you can consider some chemical actuation. In that case, many people simplify by considering impulses, instantaneous changes of velocity, but a better model would be having some kind of pulses with some fixed, not fixed, fixed level of actuation and variable duration. I will talk about that later. For the moment, consider this pulse amplitude modulated. And then minimize the consumption of fuel. You use any of these two. Actually, the L1 norm is more related to the fuel, but harder to minimize. So most people use this one. And now, what about the discretization of the model? Well, one interesting thing about the model I presented to you, which I see now, I forgot to say the name, is Hill-Klohezy-Witshire. That's the name, HCW. Is that you can solve it. This is a very easy exercise that you can actually, I force my students to do it, or I used to do that in the past. Nowadays, I don't, but I used to do it. And you can find A and B. It's not too difficult. Also, you can see that everything is either constant or periodic, except for these two terms. And they represent the only unstable mode that the system has. It's a polynomial instability, so it's a double zero. And what does it physically mean? Well, what it means is that if your chaser and your target have a slightly different period, of course they're going to drift away in time. But if they have exactly the same period, they will do whatever complicated dynamics you can think of, but they will be periodic. And actually can be proved, which is very strange, that the chaser goes around the target in an ellipse. But the target is at the center of it, it's not at the focus. It's the difference. And of course, it's not orbiting, even if it looks like it's orbiting. It's just the relative motion, okay? All right. Now, let's consider this notation for the state, this notation for the control, and let's also consider the possibility of having some disturbances to make the problem interesting. And let's assume that these perturbations are perhaps random. I mean, they could come from the orbital perturbations, who are typically not so intense, but they could come from having not great propulsion, errors in the actuation, etc. And now, let me show you one of the tricks that you can use for this kind of linear system. So remember this equation is the same I showed you before, but now including the disturbances. You can use what is called a compact notation, in which you stack the state at all times, the control at all times, the disturbance at all times, and you can quite easily define these huge matrices, A, F, G, U, and G delta for the disturbance, which can be used for the optimization procedure. Now, these were the constraints that you can put in matrix form. And since we're considering some random disturbances, we should also consider taking expectation. The expectation will be denoted by a hat, and it's taking a time k. Our objective function will be based on the expectation. That's why you will see how the disturbances go away, but you will have their mean. Now, this was a great idea. Imagine you want to do your rendezvous at some fixed time in the future. So how do you put that into your objective function? So our idea, based on this sliding horizon, is as follows. If gamma is really large, this is a step function, so it's 0 until k is equal to ka, and then it becomes very large. So as you move and you start applying the control, this ka starts approaching to you. So you start to have a very large weight on the state at the end. And in this way, this gets closer and closer. The optimization procedure is forced to rendezvous when k is equal to k more or less. I mean, you are not forcing as a hard constraint, but you are forcing with a constraint in the optimization function. We will see in the simulations. Okay, now using the compact notation, you can write the objective function, you can write the constraints, and using the prediction of the state, write everything in terms of the control signal that you can see here, and also the disturbances. That's unfortunate having the disturbances there, but we will see how to deal with them. Now we can finally, after all this effort, pose the MPC. So the MPC will be solving this problem, minimizing this objective function, which is written in terms of the actual, the present state, the future controls, and the mean of the disturbances, subject to these constraints, which are also written in terms of the future states, present state, and here we don't have the mean, we have the full disturbance. So how do we deal with this? Well, first of all, imagine you didn't have disturbances. Then we can, as I said before, use quadprog. It works like a charm, it's very fast, and it will be not a problem because the typical time step in rendezvous can be taken as 1 minute, and you solve the problem very fast, in less than 1 second. That's not an issue. But now, what do you do if you have the disturbances which you don't know about? Okay, now you have to do something else. That's called robust MPC. Robust MPC. So robust MPC can be thought in 2 ways. What if you know some bounds for the disturbance? Then what you can do is solve the constraints for all possible perturbations, which is a bit conservative, but it can be done. Then you have to solve what is called a sub-minimization problem, so to say. So before solving your MPC, you also minimize and maximize the constraints for the disturbances and find the worst possible bounds, and then you solve it. But that's too conservative. Here is the idea. So in this case, assuming you know the mean, you need to determine these guys, which will be the worst case, depending on the sign of the matrix. You will look either for the max or the mean. And here is how to do it. And this is what is called a minimization subproblem that you can have to solve. But it's very easy to do it. You just need to look at the signs of these guys, and then you find the solution. That's very easy. But very conservative. So this was our first approach, right, in 2009. And with these ideas, we submitted a paper. I was telling Manuel about this to the Journal of Guidance. We were very happy with the result, but they rejected the paper because nothing new here. Okay, but it was a great experience because they gave us two ideas. First of all, they told us, why don't you try this new chance constraint approach? That's what I'm going to tell you about. And then the other thing they told us about is, why do you consider Pule's control? So what happened is, from our rejection, we got two ideas for two papers that were published later. So not so bad, not so bad. Okay, so what about the chance constraint? Let me skip this. So what is the idea of the chance constraint? The idea of the chance constraint is, okay, assume your perturbations are random, okay? Renounce to verify them always, but assign some probability. Say, okay, I'm going to verify my constraints with a 95% probability. But you may think, I don't like that. Okay, but because you are closing the loop, you will verify them basically always. I mean, you can check in simulation. Maybe the first time, no, but later, because you close the loop, there will be no problem. And we did, I will show you the Monte Carlo simulations, and we never had an issue. So now, if you assume the perturbations are Gaussian, what you do now is try to find a constraint with some probability, and for here you can use regions of confidence for the Gaussian distribution. And as you may know, they are ellipsoids. So now what we have is a linear. Remember the problem we had to solve. Sorry, we had to solve a linear optimization problem subject to an ellipsoidal constraint. Well, it turns out that this can be solved analytically. So we didn't even have to solve this sub-minimization problem for the robust approach. And now the only thing we had to do is apply this formula that you can see here, this formula. All right. Only problem is we need to estimate the mean of the disturbances, and we need to estimate the covariance of the disturbances. So what we did was also add a disturbance estimator to the problem. And how did it work? I mean, you basically, what you do is, as you move, you notice that you are not doing what you expect to do. So based on that, you can use some formulas. I don't have time, I will have to skip. But you can use some actually recursive formulas with some memory in case something is changing, you can forget it. Some formulas to estimate the mean and the covariance of the disturbances. So doing that, and I will later give you the references if you are interested in the approach, we did some simulations to see how it worked. Okay, so imagine an orbit about 500 kilometers altitude. So you have this n, and you want to get as close as 1.5 meters. And where do the disturbances come from? In this case, we assume we have a very bad actuator model. So we have, for starters, some rotation and also some deviation from the maximum values. Why not? To see how it works. And this will not be Gaussian. So here you see what happens if you start at some point and you don't apply, if you apply the non-robust MPC, of course it works perfectly if you don't have disturbances. But you have then, it can go crazy. I mean, we use quite strong disturbances, which typically will not be the case, but just to test the controller. Here you see the chance-constrained trajectory in 3D. Here you see, I mean, the errors we had in the actuation were, I mean, quite enormous. But still, the chance-constraint was able to more or less estimate the error and this bias here that was very difficult for the non-robust MPC. And then we did was doing some Monte Carlo to see what happened with the constraint violations and with the rendezvous. And we found that even though, and this is very interesting, the chance constraint approach just gives like a 95% probability of verifying the constraints, they were always verified because the closed loop nature of the controller. In the end, the final probability of constraint variation is really, really, really small. And it also decreased the mean cost because it was able to estimate the disturbances. Here you see the simulations as you see the emission cost and the size of the disturbances, and the blue points are the robust MPC. So this was one of our more successful results. I mean, I think it's in MPC Rendezvous is my most cited paper. So quite good. Also, one interesting thing you can do is, okay, what if the disturbances come from unmodeled dynamics? And here you can see some simulations with eccentricity, and it still works. And here you see more of this with eccentricity. So in the end, you always satisfy the constraints with the chance constraint approach. And if you have a rotating target, as well. I mean, that's not too difficult to pose in this framework. You just have your constraints also changes with time. But not a big issue. Okay. I have to go fast, so just telling you what happens if you have on-off thrusters. So the main difference now, let me show very quickly. And here we also use the model with eccentricity to give it some additional difficulty, which is a time-varying model. It's called the Schauner-Hempel model, but I don't have time to expand on it. The main difference now is that our control variables, this is fixed, the level of the thrust, but you have to decide two things: when to start the thrust and how long it lasts. So now instead of having three variables, ux, uy, and uc, you have to have, for each positive and negative direction, you need to have one variable for when to start and another for the width. So in the end, you have 12 variables. But even worse, here is the matrix V. In the matrix V, you will have these parameters, and they will appear non-linearly, in a non-linear way. Now you see here this strange space here. The reason is I'm reusing the slides, I have to recognize. And we thought these integrals were not explicit, but actually they are. And it's in some obscure PhD thesis that we discovered years after we did the result. So I left this here just to emphasize that you can actually have this also explicitly, but it's non-linear. It's non-linear. So how do you deal with these non-linearities that you have in this problem? Now you cannot do as before. So what was our idea? Let me go directly to the algorithm. Sorry, everything else is the same. So our idea was as follows. It's very easy to, and this is known for many people, consider an impulsive actuation, because the only thing you do is change the velocity. And it's also very easy to transform this impulsive actuation into a pulse which more or less will approach the output of the system. So what we did, let me go fast. Here it is. The algorithm was, first of all, solve the problem for standard impulsive control. Now from there, find what is called a hot start. That will be our initial guess for the optimization. Linearize around this solution and find small differences, improving the solution, and then repeat. So at each time step, we do this iteration until either time's up or we reach convergence. If we don't reach convergence, at least we have some solution. So this is a key point. If you want to do MPC, it's very important that you're able to always produce some kind of solution. Okay, let me show you some simulations very, very fast. Let me skip the details. Here are all the details, and I can give you also the reference. Well, I will give the reference at the end. So here is what we get. Here is the real trajectory in blue. This will be the impulsive ideal trajectory, and if you transform this to PWN, to a pulse trajectory, it doesn't work. But with algorithm, we were able to transform into a working solution. That was pretty good. And here you can see, I mean, the pulses are quite small, except for this one at the beginning. But they're still pulses. They are not impulses. Okay. So let me just talk very briefly about 3 other things. I have almost no time. So I think I will skip this one and go directly to the one with UAVs. I was too optimistic, I think, with the slides. But okay. Let me skip this. It's a pity. But let me just very briefly talk about how to use this for guidance of UAVs. And this was in the context of the thesis of Francisco Gavilan many years ago, because I haven't worked much more in UAVs, so I have nothing new to show here, but still it's quite nice. So very fast, the point was, let me go to here, that we had developed first a motion planning system that was quite fast, but the trajectories that were there output were straight lines. So we have many corners, and as everyone knows, you cannot fly those. It's impossible, right? So what we wanted to do is develop a guidance system to be able to fly this trajectory. So how do you do it? Well, here are the 3 degrees of freedom equations for an aircraft. And typically people, when they discretize, they consider something like this, which again are straight lines. So it doesn't work. So what we did was consider instead having a constant back angle, something more physical, and then you get segments of constant curvature, which are more realistic and can be handled by a low-level attitude control system. If you do that, then the discretization becomes like this, and this will be how the segments will look now. So now what is that we have to develop? We have to find what is our control, or our input variables, the velocity, the flight path angle, and now this variable based on the bank angle. But of course, it's nonlinear. Okay, so what did we do? Again, you always, when you do MPC, you always have to think about that. You need to have some backup or something that you can use when your optimization procedure doesn't work. So we took a look at missile guidance law, and we implemented one which is called the L1 guidance law, which is related to proportional navigation. And we use that as a hot start for the MPC, which we optimized. We also consider wind, which was a disturbance. So we did as in the rendezvous problem and estimated the wind, and then did a successive linearization to try to improve the solution. And this, again, works quite well. So let me just tell you a few things. This is the L1 navigation law that was modified to include the load factor. I think this was a request of the reviewers, indeed. well, I can skip the linearization, and this is again. But what was interesting is how do you pose the cost function when you want to follow a trajectory, and you don't want something like this to happen because you have some waypoints. You could include them in the objective function, but you could have some oscillatory behavior. So what we did was combining three different cost functions. One, the distance to the reference flight segment instead of waypoints. So we knew we had segments, so distance to the segment. Two, the time synchronization with the waypoints. And three, avoid to use too much input. So doing that, and let me skip the details again. Of course, how to choose the relative weight. So we did some Pareto analysis for that because it was a multi-objective function. And let me show you some simulations. Here it is how the aircraft, this is in the vertical profile, can follow a step like this. You have the first iteration, this one from the L1 guidance law, but then you keep improving it until the iterations converge. Here it is something in 2D, and here something in 3D, and you can see how we have a reference which has corners, then L1 law produces something, and we improve it. We get closer to the reference trajectory, and at the same time, we spend less actuation with the predicted control. And in this case, we also had wind, which we estimated using a very similar technique to what I showed you for the spacecraft rendezvous. More simulations, and here is how we estimated the wind. I think we had some kind of random model, so we kept you keep estimating at all times in case it's changing. And we did a lot of Monte Carlo studies and so on. Again, this approach worked quite well. So let me skip. And let me just finish with another idea. And this is a bit sad because this project failed, but it was not our fault. It was because Boeing at some point decided he didn't want to be into this anymore. So they stopped working on this problem. And the project was stopped. But it was working quite well. And some people here may know about the AIDL. You, for instance, and you too, I know. This is a language that Boeing created to describe trajectories, right? But what's the problem? I mean, they are supposed to be flyable, but you need to actually fly them. And they have some kind of triggers that tells you, okay, you are, I don't know, you know much more than me, but you are, they are good for the autopilot in the sense that you can say, okay, I'm going with this ramp, and then I have to turn. So in some sense, it may remind you of what we did before. You have some trajectories that are supposed to be flyable, but they are not, cannot be directly flyable. So they needed a guidance system, and they actually contacted Eduardo, which is, I mean, as I told you, he's now an emeritus professor, but very good in MPC, and he contacted us for the aerospace part, and we were working with Michael Hart, which is he's also quite good. I don't know if he's still at Boeing, but he was at Boeing when this happened, which was 5 years ago, 2018. Okay, so very quickly, let me just skip. This is all Boeing publicity for sure, but in the end, they have this very complex set of commands to describe the trajectories. And the thing is that they have what they call triggers. And a trigger is an indication that you need to stop what you are doing and change the mode. I mean, if you reach a certain altitude, then you have to change. Things like that. So that was a challenge to implement those in MPC because we discretize the system, but the trigger can happen in the middle. So you have some kind of, you can have some kind of oscillatory behavior in the trigger prediction and things like that. I mean, we started working on that. We got several models working quite well. Let me see if I can show you some simulations that we had at the end. So, as you say, I mean, we had some problems with the triggers. And we were able to, I think this was some simulation about a trajectory. And it worked quite well. Here was, this is the kind of things that you get in the AIDL. And we were very close to the trajectory predicted by, I don't remember the name of the trajectory computation machine, but they have one. So with our guidance, and even in the presence of wind turbulence, we were able to do it. And we were prepared to actually do at least hardware in the loop simulations. We had already done some analysis of what we needed to do, and we had this, which at that year, it was quite good. Now, I guess you could do much better, but it was possible to run it in real time. So we did some dimensioning of the needed prediction horizon. This is the most practical application of MPC I have ever done, but it's a pity that in the end it didn't run because, I mean, they back out from the project. It's a pity. They were interested in other things suddenly, urban mobility and things like that. So we didn't fit. Anyways, that's life. And well, thank you very much. I'm sorry if I went too much over time. And here are many references, and I hope you got something out of the talk, at least understand how MPC works. And if you are interested in some particular application that I have done, feel free to contact me. I'll be here today. Here's my email, and if I can help you in anything, I will do it very happily. So thank you.